Hello, welcome to Project 152, your weekly specialist exam prep. So last week I gave you 5 questions to do, and this video I'm going to go through the solutions. If you go to the link in the description, you'll have next week's 5 videos. You can do those questions and watch next week's video. Click the link, you'll understand everything. Alright, these are the week 3 solutions. This is tech-free, no calculators here. Let's get started. This question. Now, on the year where this question appeared, this was the multiple choice question that students did the absolute worst in. And any other years where similar questions have appeared, people do badly in them. So if you want to shine above everyone else, be able to do questions like this because it feels like no one can do them. Now, when it comes to questions like this, there is a place that you really want to look. And it's right there, those 2 numbers. Generally, those 2 numbers will tell you everything you need to know about what we call the geometric interpretation of the solution to these equations. So when I look at this, how can this be interpreted? It can be interpreted as 1z equals 0. So if 1z equals 0, then z equals 0. Now, I could probably make a pretty meaningful guess at the answer, but I'm going to take 2 more steps here. Alright, so then once I know that z equals 0, I can sub that into the next line. So I can say negative y plus 5 times 0 equals negative 6. Alright, so that means that y equals 6, right? If I solve that for y. And then I can take z equals 0 and y equals 6 and sub it into 1, 1, negative 3, 4. So that means that x plus 6 minus 3 times 0 equals 4. And I can solve that one. So we've got x equals 4 minus 6, x equals negative 2. So what does that mean? Well, this matrix up here represents 3 equations of planes. And the solution, when we try to solve those 3 equations of planes, that system of linear equations, 3 equations, is negative 2, 6, 0. Negative 2, 6, 0. That means that the 3 planes, the 3 equations, are meeting at a single point. And that single point is negative 2, 6, 0. So which of these four pictures represents 3 planes meeting at a single point? The answer is D. Look right here. There it is. 3 planes meeting at a single point. If you're looking for like a representation of that, look at the room you're standing in right now. Look at the corner. The wall, and the floor are meeting at a single point. 3 planes meeting at a single point. And that's what that is. Okay, so I said to be able to do this question quickly, you want to look at these 2 digits right here. So what's our sort of rule of thumb here? Well, if the digits are 0 and 0, right, that means that there are an infinite number of solutions. And the picture where we see infinite number of solutions is right here. We see 3 planes along a line, right? And that's our infinite solutions because that line is infinitely long. So this is it right here. Okay, where else? Let's go with 0 and literally just any number. Any number. I'll just dumb it down here. Just 0 and any number. That means no solution. Now, in that case, no solution, that means the 3 planes don't have anywhere where they all meet. Right? You can see this one here. The planes meet each other, but there is no place where they all 3 meet each other at the same time. This one here as well, the planes are meeting each other, but not anywhere at the same time. Now, if it says 0 number, it's either B or C, and there's a future question coming up in a future 152 where we'll differentiate between these 2. But I'm not going to do it. In the comments, if you want to explain how to differentiate between these 2, do it. Someone do it. That'd be awesome. This one here, part D, well, that's a number and a number. All right? 1 solution. These are our general rules of thumb that are going to let you get through questions like this. All right, celebrate. Now, we have seen a question like this before. It's proof by induction, and it says, when using proof by mathematical induction, The inductive step requires proving one of these things. Okay, so this is, again, we did one of these in like week 1, I think. The deal with these is it's kind of hard for students to like jump into the middle steps of proof by induction because they learn it sequentially. Do this, then do this, then do this, then do this. All right, so what does the inductive step require us to prove? Well, it requires us to assume that it's true for k, right? So everywhere we see n, we substitute with k, but we're assuming that, and then we need to prove that it's true for k plus 1. All right, so let me sub k plus 1 in for everywhere where I see the letter n. So we're going to have a k plus 1 for the first n, and then brackets, and this gets sneaky, right? Because then we got 2 times, and then the n is a k plus 1 again, and then subtracting 1, and then closing those brackets, and then the last set of brackets, 2, and then another n, so we need another k plus 1 in there, and then a plus 1, and then close those brackets. So just got to be a little bit careful. Now, obviously I'm not going to, my solution, the thing I've written, that is what we have to prove, but like it's not here because like we can probably just simplify it a little bit. K plus 1 can stay k plus 1 for now. 2k2, 2k plus 2 plus 1. Okay, and then we can just maybe simplify one more step. K plus 1, 2k plus 1, 2k plus 3. All right, is that in my solutions? So I've got a k plus 1. All right, so all of them have a k plus 1. All right, so I'm happy with that. Then I've got a 2k plus 1. I'm down to C and B. And then I've got a 2k plus 3. Looks like D is going to be my solution. Okay, my only tip for this one is don't rush. Because in these questions, you always have to do like some distributive law stuff, expand brackets and things. And so it's very easy to just like make the silliest mistake by like not doing one little thing. Just write more lines. Do the actual work behind it. It's still only going to take you like 45 seconds or something to do like an extra line and make sure that you don't mess it up. Free marks, these questions, I think. Okay, next question. Okay, another question that is kind of free marks, and I'm going to smash this one out really, really quickly just by telling you the following. When you have an equation of a plane, ax plus by plus cz equals d. All right, these values here, I just changed colors and I didn't end up with a different color. These letters here, A, B, and C, represent the normal to the plane. All right, so if I have the plane, there's my plane. These represent a vector that makes a right angle with the plane. So what do I have here? Well, I have an A value of 1. I have a B value of 0. And I have a C value of -2. All right, so this vector has an equation of 1, 0, or is 1, 0, -2. Do I have a 1, 0, -2? Yeah, I can see it there. C is my answer. Done and dusted. Super straightforward. And that brings us to this question here. So imagine you're doing an external exam, you get up to question 12, so it's only the second short response question, and it's just this. It looks really big. The QCAA is trying to do you a favor though, because you can see it's like fully like 1 mark, 1 mark, 1 mark. All this A, B, C, D, E, F, it's scaffolding. The idea is that, yes, this question looks intimidating, but take it one step at a time. All right, so let's just do part A and then we'll do part B, etc. Determine a vector n that is perpendicular to the plane. Oh, that was the previous question. Like if we could do the last question, we can do this one. It's very simple. Boop, 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 boop. It's 1, -1, -2. All right, it's just the coefficients of x, y, and z. Okay, super easy. So let's do our next question here. So part B says, determine a vector equation of the line that is perpendicular to the plane and contains the point negative 2, 1, 3. Oh, okay, this is a trick question because, like, I'm thinking planes, but then it says determine the vector equation of the line. Okay, so how do we do a vector equation of a line? R equals A plus TD, where A is some point on the line, some starting point, but it's really just a point on the line. Now, contains the point negative 2, 1, 3. So I have that, negative 2, 1, 3. And then T, and then, or lambda, whatever you like, you can use either. T, and then determine that is perpendicular to the plane. So what direction is it moving in? Well, it's moving in the direction that is the same as the vector that is normal to the plane. And we literally just found that. 1, negative 1, negative 2. All right, that's part B done. Like, I've finished. So far, so good. Next bit is use the result from question 12b. So use this to express the equation of the line in parametric form. All right, I am going to do a little bit of working here just because I want to explain what's going on. We can rewrite this, if we want to, as r equals negative 2i plus j plus 3k. And then this bit we can write as plus t, and then I minus j minus 2k. All right, going a step further here, I can expand that bracket there, which is going to give me ti minus tj minus 2tk. All right, and I've still got all of that. And then I can factorize the i's, the j's, and the k's. So I can say negative 2 plus t I. Right? Negative 2i plus ti, we can factorize the I out of it, and we're left with negative 2 plus t. Same with the j's. We end up with 1j minus t j. And same for the k's. We end up with 3 minus 2t k. All right. I really am going the long way around here because parametric equations are ones that people have a little bit of trouble with. Okay. This tells you like the x coordinate of our position when we're talking about Cartesian things. So we can say that x, the x coordinate of our thing, is equal to negative 2 plus t. Just like that. We also have y is equal to this, 1 minus t, and we also have z is equal to 3 minus 2t. Okay, our answer is this. This is the parametric equation of the line. The parametric equation of the line are 3 equations that tell you the coordinates of the x, the y, and the z thing, particle, at time t. Now, did you have to go through all of this work? No, not really, right? Because you could have started here and just said, okay, now that you've seen it all, we can sort of see what's happening. The parametric equation is negative 2 plus t. Negative 2 plus 1, negative 2 plus 1t. The y is 1 plus negative 1t. There. The z is 3 plus negative 2t, which is 3 minus 2t. Just wanted to step it through, make it clear like how that logic works. Okay, I am going to get rid of this working. I might need this though, so I'll hold on to that, part D. Okay, so we have part D here. The line and the plane intersect. So we have a plane up here, and we found a line in vector form, in parametric form. Show that the coordinates of S are 2, negative 3, negative 5. All right, so with these sorts of questions, usually part A leads into part B, leads into part C, leads into part D. So they probably want me to use this somehow. Now, the QCAA actually provides 3 different methods for showing this, for doing this. I'm just going to pick the one that I guess that I like the most, that makes the most sense. I have a plane, which is this one here. So I'll just write that up. X minus y minus 2z equals 15. Now, if this line intersects with it, I should be able to find the time at which they intersect by replacing x with this, because this tells me at what time the point, it's our x coordinate. This I can sub in for y, and this I can sub in for z. So I'm going to put that there, and that there. All right, so that's done. Now we're just expanding it and solving it for t. I think anyone can expand that and solve for t. All right, so t equals 4. Now what does t equals 4 mean? It means that the plane and the line intersect at time equals 4. So the question is, have we shown yet that the coordinates of their intersection point are 2, -3, -5? No. We've shown that the plane and the line intersect at t equals 4. We haven't shown where they intersect. So now all we need to do is show, well, what is the coordinates of the line, or what are the coordinates of the plane at time 4? Now, we can't really put a time into our plane formula, but we can put a time into our line formula. So if we sub t equals 4 into here, x equals -2 plus t, which is 4 here. So -2 plus 4 is 2. Doing it again for y equals 1 minus 4, y equals 1 minus t, t is 4, so -3. And doing it one more time for z, 3 minus 2 times 4, 3 minus 8, -5. At time 4, the coordinates of our line are 2, -3, -5. And I think that we can wrap that up. Neat little bow, QED. The intersection point of our line and our plane are 2, -3, -5. Done. Okay, we've still got a couple of parts to go. Now, I just double checked. The next two parts are relatively easy, and after telling you like each step relies on the other parts, we actually don't need any of the other parts to do the next two parts, so let's get rid of all of this. And we'll just bring the whole question back. Okay, something like that. And just so you're not getting too confused now, we're doing part E. Oops. Might need to work on that. Alright, it says determine vector AS. Super straightforward, right? Vector AS is going to be equal to vector OS minus vector OA. Now, vector OS, show that the coordinates S. Alright, so the coordinates of S are this. So vector OS is literally just that. 2, -3, -5. And vector OA, we've got a point A. And so OA is that. Which means that AS is just do that. 2 minus -2 is 4. -3 minus 1 is -4. And -5 minus 3 is -8. Alright, that's part E done. And then part F. Use a property of parallel vectors to verify that AS and N are parallel. Oops, I really should have kept determine a vector n that is perpendicular to the plane. I should have kept that. All right, let me bring that back. All right, there it is. So reaching there, we need to prove that this AS is parallel to that. Okay, so how do we prove that two vectors are parallel? Two vectors will be parallel if one of them is a multiple of the other. Right, so U is parallel to V if V is equal to some multiple of U, or vice versa. So we just need to show that that is some multiple of that. So I think we can do this super fast. We can just say that AS is equal to 4, -4, -8, which is equal to, I can like factorize it, 4, 1, -1, -2, and look at that, right? And I guess to like just to put a pretty little bow on it, I can say that 4, and what are we calling that? We're just calling that vector n, aren't we? So we're saying that vector AS is equal to 4 times the normal, therefore parallel. Therefore parallel. Okay, that was question 12, so the second short response question that you'd get. 8 marks in it, but all very like, do this, then do this, then do this, then do this. Okay, big celebration at the end. Last question. So, last question here, this is question 16, so it's a bit further on in the paper. Gaussian elimination and kind of leads back from that multiple choice question we did earlier. All right, part A. Use a Gaussian technique to determine the value of lambda for which this system of equations has infinitely many solutions. Yeah, definitely from that multiple choice question. Okay, so how am I going to go about this? Well, it says use a Gaussian technique, so it feels like I've got to put it into a augmented matrix. They've made this really gross. So I think that in order for me to deal with this, I really should just rewrite it in a way that's nicer so I don't make any mistakes from the start. X, Y, Z, constant. All right, so I've done it. The X, the 5Y, and then negative 2Z. So I've moved that 2Z to the other side, equals 1. And then I've done the same here, rearranged it to X, Y, Z, and equals 3. And on the bottom one, I wrote 0x because there's no X's here. 8y minus 3z, and then lambda is our constant. All right, let's take that, bring it down into an augmented matrix. Okay, there it is. Nothing special happened here. X, Y, Z's, and the constants. Now, they've been pretty kind here, I think, because we've got a 0 sitting here. Because remember, first goal, Gaussian elimination, make this a 0, make this a 0, right? So I don't have to do anything to row 3 in my first step, but I do need to do something to row 2 to turn this into a 0. All right, so let's do it. This 1, 5, negative 2, 1 up the top remains as it is. And then the question is, what do I have to do to row 2 to get this to be a 0? I need to subtract row 1, right? Because if I do row 2 minus row 1, 1 minus 1 will be 0. So the new row 2 is going to be equal to the old row 2 minus row 1. And I always mess this up. All right, so 1 minus 1 is 0. Negative 3 minus 5 is negative 8. 1 minus 2 is the same as 1 plus 2, which is 3. And 3 minus 1 is 2. All right, and nothing happens to row 3. 0, 8, negative 3, and lambda. I see something interesting happening in our future. Let's see where it goes. So the next step here is to look at these values, and because we need to turn this 8 into a 0. And then the question is, how can I manipulate row 3 using row 2 so that this becomes a 0? I could add them together, right? Because 8 plus negative 8, that's going to be 0. All right, they have been really kind to us. So I've just done the first 2 lines, nothing interesting there. But the new row 3 is going to be equal to the old row 3 plus row 2. And so we can do addition, that's not a problem there. So 0 plus 0, not surprisingly, 0, that should always happen. Let's look here. 8 plus negative 8 is 0. Negative 3 plus 3 is 0. And lambda, and this is where you've got to be a bit careful with these like variables inside Gaussian elimination. Lambda plus 2 is lambda plus 2. Okay, done. We've done our Gaussian elimination. Now the question is, use a Gaussian technique to determine the value of lambda for which this system of equations has infinitely many solutions. So, you should remember, hopefully, from that question 3 questions ago, that we're going to get infinitely many solutions if the last 2 things, this thing here and this thing here, are both 0. 0, 0, that means infinite. Let's do the infinite sign, infinite solutions. Okay, so very, very simple. We need that, because that's already 0. We just need that to be 0, right, for infinite solutions. For infinite solutions, lambda plus 2 needs to equal 0. So that means that lambda equals 2. That's it. I think I did it. That's part A. Part B. So part B says, use the result from question 16a, there's our result, to determine the infinitely many solutions. Express your answer in the form of a vector equation of a line. All right, so if we know that there's infinite number of solutions, we can find those infinite number of solutions. I'm just going to write up the matrix one more time, but subbing in 2 for lambda in here. So just to be very clear, I've taken this matrix and I've just rewritten it here, but with negative 2 plus 2 being 0, so I get this thing here. All right, so when you get this infinite solution 0, 0 thing going on here, right? What that means, we're going to rub this out in a second, but 0z equals 0. Z could be anything. Z could be 1, Z could be 2, Z could be a million. So because Z can be anything, we let Z be a parameter. I'm just going to let Z be K. Now, once we've decided to let Z equal K, we can sub K in for Z here and here. Start solving these in the same way that we've solved them previously. So we can say negative 8y plus 3k equals 2. Right? And then we can solve that for y equals, just to rearrange it. All right, so rearranging that, I get y equals 2 minus 3k over negative 8. Now that I know that z is equal to k and y is equal to this, I can sub z equals k and y equals that in here and solve for x. So let's do that down here. So 1x, so x plus 5 times what we believe y to be, which is 2 minus 3k over negative 8, minus 2z, which is k, equals 1. And from this monstrosity, we can like expand and simplify, and we'll get x equals something. I might actually do this on camera because this is one that people have a little bit of trouble with. X plus 5 times a fraction is the same as 5 times the top of the fraction. Some people do like 5 times this and 5 times this. No, it's 5 times 2 minus 3k. And then it's kind of like this. And then we're going to take that and divide the whole thing by negative 8. Just like that. And then this negative k, let's just put it over the other side, maybe 1 plus 2k. All right, from here, we can just take all of that and like bring it to there. All right, so pretty gross, pretty weird, because I brought this plus this, but because there's a negative 8 there, it's actually like negative this. And when I moved it over here, it becomes positive this. So get rid of the negative there. What I can do, and I'll just do it in this line, is expand this. So I'm going to end up with 10 minus 15k. And it really is a test of our algebraic skills here, because now if I make everything be over 8, I can bring it all together. So 2k is the same as 16k over 8, and 1 is the same as 8 over 8. All right, so now it's all over 8. Pretty neat. Great, it's all over 8. And now I can like group my like terms. So 8 plus 10 will be 18, and 16k minus 15k will be k. So all of that heavy lifting there, I did like 5 lines and just kind of did it all and erased it. But after all that algebraic manipulation, we have 3 very important things. We have z equals k, we have y equals this, and we have x equals this. Let's put that up there. Now that right here is the parametric equation of our line. That is the parametric equation of the line where these 3 planes meet if there are infinite many solutions. We don't want the parametric equation of the line. We want the vector equation of the line. So let's turn this into the vector equation of the line. So there's a few different ways that you can go about this, but I'm going to sort of do it and explain what I'm doing here. So the vector equation is equal to 18 plus k on 8, I, plus 2 minus 3k on negative 8, j, plus just z equals k, right? Plus k. Oh, that's confusing. Hopefully we understand that this k is a parameter and this k is our k, our vector direction. All right, so I'm not sure how the QCAA would feel about us leaving it like this. An argument could be made that this is the vector equation of the line, right? Because I can sub in k values and it'll give me coordinates I, j, and k components. It's probably not what they mean. It's not what their solution looks like. So in order for us to have a vector equation of a line, it's generally considered, I guess, good manners for it to be in the form a plus td, where a is just some point and d is the direction that it's moving in. For us to do that, we're going to have to like separate the 18 and the k, right? Get the k's out and get the constants out. All right, so how can I do that? We have 18 plus k on 8. That's the same as 18 on 8 plus k on 8. All right, 18 on 8 is the same as 9 on 4. All right, so that now, this bit here is our i's. All right, and we'll do something with it in a second. All right, this is the same here. So we can have 2 on negative 8. So if I go plus here, 2 on negative 8 is negative 1/4. And negative 3k on negative 8 is positive 3 on 8. Okay? Now all of that is our j components. And then we are left here with our k components. Now how can we deal with that? It's just k, right? It's just k. And we're adding it right there. Okay, final step. We are done here. We have 9 on 4 I, negative 1/4 j, and no k, right? 9 on 4 I plus 1 or plus minus, so really it's just a minus. Minus 1/4 j. And that's our starting position, right? Because the rest of them have our parameter there, our k parameter there, and they're going to be our directions. So then plus, and then k out the front, and then the I, the j's, and the k's. Very confusing with this k. I wish I'd chosen t. All right, k times what makes k on 8? 1 on 8. And that's the I, and then 3 on 8, and that's the j, and then k times what makes k? Just 1. And that's our k component. So just 1k, which is k. That is the vector k. All right. So I think I'm done. This is the vector equation in this nice form, starting position and like a direction. Done. We can probably avoid some of our confusion if we don't use this notation. Instead, we use like column vector notation. So an alternative solution, and probably like a neater way to go, would be starting position 9 on 4 minus 1 on 4, 0, right? I, j, and then no k, plus the parameter 1/8, 3/8, and 1. This is good. That's pretty neat. All right, I'm starting to run out of space here, but we are done. I love it. Celebrate. And that is it. Week 3 solutions done. Go into the description. You'll find the link to the next set of questions. They are tech active, so make sure you're using your calculator. If you watch week 2, you'll know we're using our calculator a lot. We've got to get used to it. I'll catch you in the next one.